Anyways, I am doing the review anyway. So the last time we started doing the history of operating systems, and now today we are continuing on it. Okay, so we are going to do this a lot, looking at the history of the operating system. That's going to explain a lot to me, because nowadays, I mean, the operating systems got very complex. Most of the stuff they are doing, they are actually not part of the operating system itself. So it is better to look at the original, the main idea and the problems that they try to solve it. Okay, I think we looked at this the first era, the 10 years, the initial computers, the electronic computers. Okay, the vacuum tubes. Okay, question for you. We say that in the first generation computers, there were no operating systems. Can anybody tell me why? Why they did not use any operating systems at all? Don't tell me that they are not invented. Okay, everybody knows that. But why didn't they have the need of an operating system?
Because any software weren't invented of that time.
Well, it is not a very genius idea to invent operating system, right? It is you abstract away the details of the hardware, manage the hardware, and etc. It doesn't take a genius to make this invention. Why didn't they attempt to build an operating system? I mean, we are talking about machines that cost tens of millions of dollars, right? Very smart people working on it.
Machines are not able to run an operating system.
Exactly. Why do you say that, Ozan?
Because they are not able.
Because they are not powerful enough.
Yes.
Well, they are powerful enough to run complicated computations, but they are not powerful enough to run both of them at the same time, right? Because operating system has to be in my memory all the time, along with my programs. And those computers those days, they simply didn't have enough memory to hold more than one program at the same time. Okay, and if they hold it, they didn't have CPU to do all those things at the same time. Okay, that's why they didn't have any operating systems. Okay, in second generation computers, when they invented in 1950s the transistor, okay, transistor is the enabling technology for whatever we are using, because I can make the why the first computers are so weak, not powerful, because they are using vacuum tubes, and vacuum tubes are large, they consume lots of power, and they break all the time, right? So the computers become very expensive to buy and to operate too. You need many people to operate a single computer. When they invented transistors, now our chips are getting smaller and they are more reliable. They don't produce as much power. So our computers are getting faster and more capable, okay? So the second generation computers, they started doing this. Expensive computer, it just takes the input from an input tape. There's an output tape. And this system tape contains what? What does the system tape contain?
Computing, sir.
Say it again.
The data for the data to be computed.
No, the data to be computed is in the input tape. Input tape comes from the card readers, and all my data and instructions are read to through the tape drive to the input tape. Then somebody takes the input tape to the computer. Okay, Çağdaş. Çağdaş, are you going to answer my question? No. What does the system tape include? What does it include?
Libraries for computation.
Libraries for the computation. Yeah, libraries. Yeah, that's true. Okay. Along with the libraries, actually, they contain the compilers. Okay. Remember how, okay, this one says that this is a deck of cards. Okay. So my job is this. This is my name. Okay. This is my job number. And I'm going to use the Fortran compiler. Whenever the computer sees this card, okay, this input, it immediately loads the Fortran compiler. It compiles it, and then you run it, and this is the end. When you run your program, your data at the end of your program will be put to the output tape, and that output tape will be transferred to the cheaper computer again, 1401. And that cheaper computer job is to take that tape and print out the results. Okay, that way this computer is always busy because reading the input tape is easy, but doing the computation takes time. Writing it to the output tape easy. So this one is busy most of the time doing the computation. This one is busy most of the time doing the printing. This one is busy doing the input stuff. Okay, so I keep, the important thing is this one. Okay, this is a fastest computer, cheap, not cheap, expensive. Well, not any of them are cheap. They are all expensive in today's money. But for those days money, I mean, 200,000 lira Turkey US dollars is cheap compared to 10 million. Okay, so this is not an operating system, kind of a primitive version of an operating system, like the system libraries and etc., but not an exact operating system. So this is the second generation of computers that relies on the punch cards. As you see, there are no terminals, there are no keyboards. Okay, all you do is you get your cards, empty cards, and you punch them. Well, there are kind of a keyboard kind of terminals to punch your cards for you. You type a letter on the keyboard and it will punch a letter on this card. We don't call that a terminal. Or you can punch your cards with your hand using some kind of a scissor or some kind of a pin or something. Okay, then we started having this idea of why don't we have another program help me run this program? Okay, so that was the idea. Previously in the first generation computers, whatever your end program is, we just run it. Later they realized that I can use the computer to write programs, and they invented the assembler. Okay, that's the assembler. Let me make it a little bit. Okay, they invented the assembler. What is the assembler? Can anybody tell me what the assembler is?
It's the nearest language to the machine code. It's a hexamal, I think in a hexamal syntax.
No, that's the no, it is not in hexadecimal. You mean it uses the hexadecimal addresses? It is the, yeah, what you are saying is correct. It is the closest language to the machine code. Machine code is what machine is running, right? Assembly language is very close to machine code, but instead of using hexadecimal numbers to write your code, you simply have names for each instruction, and you have branching help by labels and etc. So it is almost as simple as primitive as the machine code, but it is more understandable by a human being because it doesn't use the hexadecimal code. And I can easily edit it. I can insert some instructions, remove some instructions, and etc. So that's the assembler. The assembler is a program. It takes an assembly program and it produces the machine code. So when people realize that this can happen, okay, that was the first initial versions of computers helping themselves. We are using software to write software, okay, and the compilers were not there yet. It is just the assembly stuff. Okay, then we came to the third generation. Okay, now we started having operating systems because our computers are large enough, okay, powerful enough to offer us large memories to hold many programs at the same time. Okay, we have multi-programming, spooling, time shading, and multics. Okay. Multics is the ancestor of Unix operating system. Okay, we'll talk about Unix a lot, and as you know, Unix is the ancestor of the Linux operating system, and the Linux is the ancestor of the Android operating system. Okay, most of the things that we are running today on our computers, okay, it is based on Unix or Multics variations. So many ideas were invented by Multics. Commercially, it was not a successful operating system. Commercially, it didn't sell very well. It did not get very popular, as popular as Windows or Mac OS 10 or the Android operating system, but introduced lots of ideas. So we will be looking at the Multics case a lot. Okay. So let's look at these ideas. Multi-programming means having more than one program in my memory. It is like this. This is my memory, the whole memory. I have 3 programs loaded in my memory. As the 4th program, I have the operating system. Okay. This is called multi-programming. And if this is my CPU, these 4 programs has to use the CPU, has to share the CPU in a multiplex way, in a time sharing way. Okay. If this is my timeline, this is what happens. Okay. Operating system uses the CPU. Operating system says that, okay, I am done with using CPU. Now I am going to let this job 1 take the CPU. This is time passing this way, time. Okay. Now job 1 is using the CPU, but job 1 has to stop using the CPU, otherwise job 2, job 3, and the operating system can't get the CPU, right? So how does that happen? Operating system knows that there are 3 more programs in the memory and they have to be run. That's the task of the operating system. So I say that I am done. I am going to let job 1 take the CPU over. But job 1 doesn't know that, and it shouldn't know that, there are more programs in the memory and they have to run. They have to use the CPU. So how do I switch back from J1 to job 2 or job 3 or the operating system? Does anybody have any ideas?
I think
Using timer.
Say it again, Ömer Faruk.
I think the operating system interrupted the job 1 by using timer, as my friend said, and switching to other processes.
Yeah, kind of, but remember, while job 1 is using the CPU, it uses the CPU. Operating system doesn't have the CPU. Operating system cannot take the CPU away because operating system is sleeping now. Either, I mean, 4 of these programs, one of them is running at the same time. You cannot have more than one program running. While job 1 is running, it is running in the user mode. It cannot do whatever it wants. Okay, but it has the CPU and it keeps running the instruction. For example, it is in an infinite loop, right? It does this, okay? Nope. Okay, no program, no process, and jump label 1, and label 1 is here. If I keep doing this, all the time as a job 1, I am in an infinite loop. I will never release the CPU because I don't care. I think that I have the whole computer to myself and I am running this infinite loop until this computer goes down. Okay, so what you're saying is correct. Operating system has to come back, but how is that going to happen? For that case, we need to have some kind of hardware help. Okay, some kind of hardware help. We are going to use interrupts. Interrupt is a hardware feature, okay, especially the timer interrupts. Like Ömer Faruk said, when they happen, when the timer interrupt happens, CPU stops whatever it does, and operating system takes the control again. Okay, so after a while, maybe in 20 milliseconds, okay, interrupt will happen, and that interrupt will be handled by the operating system. And now operating system is running, and operating system, after it runs, it handles this interrupt, and it say that, okay, I am going to let somebody to take the CPU. It could be job 1, job 2, or job 3. I don't know. So it made this decision job 3. And then the same thing happens. Then the operating system takes over. Then it is job 2, maybe. Okay, it goes this way. This is what multiprogramming is. Okay, this is what multiprogramming is basically. There are more details to it. Basically, this is what the multiprogramming is. So as you see, I am using the CPU. The programs are using the CPU in turn, and there are lots of switching back and forth between the operating system and the jobs. Okay, and usually switching is expensive. Switching from one job to another job, from operating system to another one, is expensive. Can anybody tell me why switching from operating system to a job or job to operating system is expensive? You should know this from your. You should know this from the knowledge of the system architecture, computer architecture.
It causes cache miss.
Who talked?
Ibrahim.
Okay, Ibrahim, say it again.
It causes cache miss.
It results in cache miss. What do you mean? That's true.
So we have caches in CPU.
Yeah.
For 3 job, there are data and different data. When you change one job to another job, you have to refresh the cache.
Yeah, exactly. When you switch from one job to another job, all the cache entries, many of the cache entries are invalidated. They are not valid anymore. I have to populate the cache again, load up the data to the cache again. So that means lots of cache misses, and cache misses are expensive. So it is more efficient to keep running the same program. But in that case, I won't have more than one program running in my computer. And we are going to see why multi-programming is so useful in a few minutes. So for the multi-programming to happen, okay, we have to have the switching, and switching is expensive. So we have to find a trade-off, okay? You don't want to switch too often. You don't want to switch too late. So you have to find a balance. That's the task of choosing your parameters for your operating system. Okay, let's go back. Let's talk about this again.
Can I ask
Not-
you a question?
Sure. Who talked? Oh, okay, sure, yeah.
Hocam, I don't get what interrupt and timer are interrupt and timer values pre-assigned? Does the operating system set the transition of time from job 1 to job 2 in advance, so that this task will not run for longer?
That's a very good question, Oz. That's a very good question. Remember what we said about the types of hardware that we had? Okay, maybe I should go to this example. Yeah, maybe this is a good example. This is the simplified architecture of our computer system. Okay? Simplified architecture of our computer system. I have my CPU, I have my memory, I have my video controllers. They are all connected to the same system bus. And there is another I/O device, there is another device, it is called, okay, clock, system clock or timer. Okay. Usually, accessing the timer, it can be done only in privileged mode or in the kernel mode, okay? Only operating system can program timer. The task of the timer is to cause interrupts, to interrupt the CPU, from whatever it is doing, and give the control back to the operating system. When the timer interrupt happens, CPU stops whatever it is doing, and operating system takes over, okay? Without the timer interrupt, maybe that job is going to take the CPU forever. We don't know. And only the operating system can program the timer. Operating system say that, okay, you are going to produce an interrupt, timer interrupt at every 20 milliseconds. Okay, that means what? Operating system is guaranteed to have the CPU at every milliseconds, 20 milliseconds. Okay, that's why it is always in control. Okay, let's say if there is a program written by somebody, by mistake, it is in an infinite loop, it doesn't end at all. But we are not clueless in this case. Operating system knows that I can take the CPU, and in fact, if that program is behaving badly, doing bad stuff, operating system can kill that process, that job. Okay, so other than the operating system, where is that? Okay, other than the operating system, nobody knows that there is a timer. Nobody can program the timer. Only operating system knows about it. Did I answer your question, Oz?
Yes, thank you.
Okay, that was a very good question. I hope everybody understood it. Oz, can you ask the question again?
Are interrupt and timer values pre-assigned? Simply.
Yeah, exactly. And it is done by the operating system. And since those values are very critical in terms of system performance, okay, in terms of system performance, they are very critical. Usually they are assigned by the designers of the operating system, but some operating systems, they say that, okay, I am going to let my administrator, to adjust the timer interrupts or adjust how many milliseconds I'm going to use the CPU, etc. Okay. So this idea of multi-programming was invented during those days in the 1960s, because now they have enough memory to hold many programs at the same time. And the CPUs are fast enough to do this switching from one process to another process. And it looks like my computer is running many programs at the same time. In fact, there is only one CPU, only one program can run. Okay, so that's a good thing. Why? Because still, I mean, I am saying that the computers are getting cheaper, but they are costing millions of dollars because we make them larger and larger, right? So you don't want to waste any CPU time. So what am I going to do? So the thing is this. The picture that I showed you a little bit before is kind of a little bit misleading. If job 1 started running, it cannot, most of the time, it cannot use, it is assigned 20 milliseconds most of the time. Why? Because job 1 will need some data from an I/O device, for example. Let's say job 1 needs data from the desk. Okay, job 1 needs data from the desk. And who is going to read the desk? Of course, the operating system. Okay, job 1 will ask the operating system to read the disk data and bring it to me. But reading the disk data is so slow. It is 1,000 times slower than, or million times slower than reading the data from the memory. So what am I going to do? Operating system says that, okay, I am going to get that data for you from the desk. Okay, so job 1 asks the operating system to read the disk and get some data. Operating system is running now, but operating system will not wait until the disk data is ready. It says that while the disk is retrieving the data, I am going to let job to take the CPU. Okay, so job 2 is going to do the same thing. Maybe it's going to say that, okay, I am going to print some data to the terminal. Again, that's a very slow process too. Okay, so that's going to ask the operating system to print something, because neither job 1 nor job 2 has direct access to the printer or the screen. Okay, they will ask the operating system to do those things for themselves. Okay, so operating system always comes in to provide these kind of services. Remember the main task of the operating system? It says that I am going to abstract away the details of disks or terminals or that kind of stuff. So all I am doing as a job 2 is print this out for me, operating system. Okay, and operating system says that, okay, it's going to take time. I am going to in this case check if the data from the disk is available. Yeah, it is available now. I'm going to switch back to J1. So what I'm saying is that in this scenario, most of the time, I don't need the timer interrupts. Because before the timer interrupt happens, job 1 or job 2 or job 3, okay, they stop by themselves already, because they will ask the operating system to do something for them. Okay, that's what happens. That's what happens. So what I'm saying here is this: Since mainframes still cost millions of dollars, okay, when they ask the operating system to print something for them, to do something for them, they are blocked, right? They cannot do anything. They cannot go on. They have to wait. While they are waiting, I should not waste the CPU time. So let's do this multi-programming. Let's load more than one program to my memory. When one or two programs is blocked, I will let the other program run. When the other program is blocked, I will let the other program run. Okay, so that way I am not wasting even a single cycle of the CPU, expensive computer. Okay, so that's the thing. That's the thing. And the other thing is, with this idea, I can save the cost of I/O computers. Can anybody tell me what this is? What do you understand from this sentence?
I think because I/O devices doing their job slowly, so they cause the CPU waste time or keep it idle. So this system enables to save the cost of I/O computers.
But it says that I am getting rid of the I/O computers. It says that I don't need these two computers anymore. That's what it says. How come? That's what it says. Save the cost of I/O computers with the idea of multi-programming.
So no need to the other 14001 devices. All jobs are being done in the same computer. I mean, I/O devices in the same computer.
Well, yeah, exactly. Yeah. Like what you are saying, exactly. I mean, I don't need this computer anymore. I can connect my card reader to this computer, and I can connect my printer to this computer. There is a card reader program running on this computer, and there is a printing program running on this computer. There are other programs running on this computer. They are all running at the same time. It looks like they are running at the same time. But when the card reader runs, okay, it says that I need this character from the card reader. So it is blocked most of the time because mechanical devices are millions of times slower than the computers themselves. So it's going to wait a lot. But while it is waiting, this computer will say that, okay, I'm going to let the other program run, use the CPU. When the printer program runs, okay, it prints something. Printing is very slow. You have to wait until the printer is ready for each character. So while it is being blocked, this computer will say that I am going to run other programs. So that's the benefit of the multi-programming. I don't need this computer anymore. I don't need this computer anymore. I am going to run everything, including the input-output jobs, including the useful jobs, on this computer itself. Okay, that's what we say the computer cost of I/O computers. Okay, so CPU will never be idle. It is always busy with something, either doing the input job, output job, operating system job, or useful jobs, whatever they are. So that's where it comes the efficiency with multi-programming. Okay, so multi-programming is that, and when you do the multi-programming, you have to be careful about this memory protection. So if I have 1, 2, 3, 4 jobs, job 1 should never be able to access the memory of the job 2 or job 3, right? So either by mistake or by coincidence or by accidents or intentionally, if I keep modifying the job 2's memory, job 2 will crash, right? But that's not a good thing. So I should provide, as a computer system, memory protection. When the operating system switches, okay, from job 1 to job 3, it sets up necessary hardware, memory management unit, memory management unit, MMU, okay. It sets up the MMU in a way that job 1 can access only its own memory, not anywhere else. Or job 3 can access its own memory, not anywhere else. Operating system runs in the privilege mode. It can do whatever it wants. But the others, they are restricted to their own space. What if the operating system by accident modifies the memory locations of the other jobs? Okay, well, that means that you have a buggy operating system that causes the system crashes, actually. Okay, that's not a good operating system. And unfortunately, well, our operating system nowadays are very robust. Okay, but unfortunately, that wasn't the case, especially for the weak computers like the early day PCs. You had lots of system crashes in those days because operating systems were very primitive. Also, they didn't get enough help from the hardware to provide this protection, because protection doesn't come cheap. You need some help from the hardware. Okay, sometimes you don't get that help, then in that case your operating system keep crashing all the time. So memory protection invented in those days. What else? We talked about the interrupts. Okay, if some hardware needs attention, if the disk drive say that your data is ready, okay, that causes an interrupt. Interrupt means that stop whatever you are doing, an operating system takes over the CPU and it handles that interrupt. That interrupt could be a simple keystroke on your keyboard, or a timer interrupt, or a disk interrupt, or a network interrupt. There are many interrupt types, you know, most of those. How about virtual memory? Virtual memory is this, okay? Each job running on my computer, they think that they have their own memory, and that memory address starts at address number 0, okay? It goes to some large number. Remember your C programs, okay? Remember your C programs. Address number 0 is null, right? Null. And you are not allowed to write anything to that address number 0 because that's a special address. And after that, all of your variables are stored at upper locations. At the top, you have your stack, and right, it is growing downwards, your heap growing upwards, and etc. That's what we tell you all the time. All the C programs behave this way. So what does that mean? How many address zeros do I have? As many as C programs running in your memory? No. That's because each C program running would think that it has its own contiguous memory allocation. It is given by the operating system, and I am free to use this all the time. So this is called virtual memory. In fact, what's happening is this. What's happening is this. At the bottom, I have my operating system pages. Here, I have job 1, page 1. Here, job 1, page 2. And this is job 2, page 1, job 2, page 2, etc. Okay, if I have let's say if I have divided my job one memory into two pieces, to one page one and page two, okay? In the physical memory, they are stored in non-contiguous way, but in logical memory, that program thinks that I have this memory for me. But in the physical world, it is a little bit different, okay? So remember the definition of the operating system. What did we say? We said that it extends or virtualizes the underlying hardware. That's what we mean here, okay? It virtualizes the memory in a way that each program would think that they have their own contiguous memory. So it is easy for you to write program in that case. You are writing programs thinking that you have your CPU and you have your memory. Well, in fact, you are sharing your CPU and your memory with some other people. Okay, good. Any questions so far? Okay. Well, if there are no questions, I think I will stop at this point. Let's take some break. 15 minutes. 9:35. Let's be here around 9:35. Okay. So with the invention of all of these ideas, memory protection, virtual memory interrupts, okay, with the help, hardware help, okay, for the memory protection, we need memory management unit. And for virtual memory, again, memory management unit. For the interrupts, we have the interrupt generation hardware and interrupt handling hardware. And operating system knows all about those, okay? For the memory protection, virtual memory interrupts, only operating system is authorized to use all those functions, all those hardware capabilities. Okay, so again, this is what's happening with the third generation computers and the operating systems. Multi-programming, as I said before, I'm running several programs at once. And I, of course, need to protect each one's memory against others, memory protection. One program needs to do I/O. That means that program cannot continue until the I/O is complete. Okay, and I'm going to let another program use the CPU. Doing I/O is expensive. It takes lots of time. But because of the multi-programming, I don't have to wait. I can run other programs. Or I can do, let's say, I have two programs running and they don't need an I/O. They need lots of CPU time. So in that case, I am going to preempt a CPU bound program. That means what? I will use the hardware interrupt, the timer interrupt. When the timer interrupt happens, as an operating system, I take over the CPU and I let another program use the CPU, even though that program is not blocked, even though that program still needs to use the CPU. And this daemons, the idea of daemons, okay, is used for spooling. Spooling is simultaneous peripheral output online. That's what makes the I/O computers go away. There is a printer spooler. Okay, there is an input spooler and etc. So it's a special job. It's a special process. Belongs to the operating system, and it just waits there, empty without doing anything. It is blocked. Whenever I need to print something to the printer, the operating system tells me to print it, and I start running. And from time to time, I'm going to be blocked because the printer is very slow. But that's okay because operating system is going to use the rest of the CPU time for other purposes. I mean, if whatever computer you are using, if you look, let me try to open up my task manager on this. Okay. Where are my processes? Okay, you can't see them, right? Let me try to see if I can. All the details, yeah. Okay. So I am going to switch. I am going to switch from that one to, maybe I can share my whole window. Yeah. You see my task manager, right?
Yes.
Do you guys see it?
Yeah.
Okay. In my task manager, okay, I have literally hundreds of programs running. Some of them are several copies of the same program. Okay. And it looks like CPU wise, my CPU is 90% idle. Okay. My Teams is using some of my CPU. But as you see, many of the programs, these are some daemon programs. Okay. They are waiting something to happen. When it happens, they will handle it. Okay. They will wait until, see this one. If let me see, yeah, okay. So Windows services, these are daemons. Okay. It is waiting. It is how much memory it is using right now. It is not active, but if something related happens, this will wake up and it will handle it and it will go back. This is all possible. This is all possible because of the multi-programming. Okay. And this is my memory, how much memory each one is using. Okay. Can I go into the detail of this thing? With this? No, I couldn't. I'm trying to get how much time I have used, etc. Let me see. Okay. Let me try to go to this one. No. Well, okay. These are the active processes. The operating system, see this one? All this information for each of these processes is kept by the operating system. And operating system has to keep all that information, statistics, bookkeeping, okay? It has to know how much CPU this one is using, how much memory it is using, okay, how much of the disk I/O percentage is used by this program. Also, what percentage of the network connections I am using. There are many other things that I can list, but I'm not going to do that. It needs all of these data. It keeps all of these statistics so that it can be fair when it assigns the CPUs to these tasks or when it assigns the memory to these tasks. You don't want to be in a position that one of your tasks is using 95% of the CPU and 95% of the memory. Rest of them are starving for some resources. Okay, so the operating system has to know about all of these. Do I have this that? Well, maybe this one. Yeah, this one is nice too because again, these are nice for the visualization, but the operating system needs this anyway. Okay, so this is my memory. Let's look at this one. It says that I have total of, okay, I am using 12 gigabytes of memory right now. Okay. And out of those 12 gigabytes, actually, I am keeping maybe 3 gigabytes as a cache. It is immediately available, I can use. Okay. It's a cache memory. And what else? Let's do some experiment. Let me close my Chrome. When I close the Chrome, see, I close that application, but my memory did not, my memory usage did not change much, right? See, it increased maybe a little bit. So how could that happen? I am closing an application. I am taking it out of my memory. My memory usage doesn't drop. Let me try to open some pages like this. Okay, more pages and more pages. Okay, that's good enough. So I opened lots of pages. So this usable cache memory is decreasing, but the overall memory that I am using is not increasing much. And it does this going up and down. Do you know what happened? Can anybody guess what's happening?
Hocam
I mean,
çoğu because most of it is cash. I think whenever you close an application, it puts more cash in its place. Maybe.
well, you mean the cache amount dropped from 3 gigabytes to 1.8 gigabytes, but the memory I have used for those programs, let's see how much memory I use for the Chrome. Yeah, Chrome is using like 1 gigabyte of memory, around 1 gigabyte of memory. Let me close that Chrome thing. It will go away, and exactly this time, yeah, it gave back all that memory to the use one. So usually you don't understand what's going on because of the virtualization. When I say load this Chrome application to the memory, it doesn't keep everything on the memory. It keeps some of it on the disk. Whenever it is needed, it swaps back and forth. We will talk about this kind of stuff when we look at the memory virtualization. Okay, so today's modern operating systems are very complicated, very sophisticated. Okay, and if I add up all the processes, the memory requirement of the processes, they will be larger than the total memory available. In fact, they will be many times over than the total memory available. So they are sophisticated enough to keep only the required parts in the memory. The rest of them will be on the disk. But the application itself will not know that. Chrome application will not know that most of its memory is on the disk, not on the memory. Okay. So these are all because memory protection, virtual memory, virtualization, and multi-programming. And they were all invented during the third generation operating systems in 1960s. And then came the 1980s. The main development here is the large-scale integration. Transistors getting smaller and smaller. When the transistors are getting smaller and smaller, remember these computers, these cheap computers, they are now cheap enough to be sold at 5,000 US dollars. So that means what? Small businesses and home businesses can buy computers. When they come computers, okay, when they buy computers, they will try to run stuff that will never run before, like the games or the home accounting or the word processing and etc. Okay, so the whole application suite, whole application set has changed. Things are different, and we need new type of operating systems. Okay, so in 1980s, IBM was a very big player. It was like a government during the 1970s, right? It's a very big player. IBM decided to release IBM PC. Before IBM released IBM PC, nobody in the business world used a personal computer because they said that they are for the kids, they are for games. When IBM released the PC, IBM PC, it needed an operating system, and Bill Gates of Microsoft, he didn't have any operating systems. All he had had a basic language interpreter. Okay, so he bought the another operating system from somebody, and he sold it to IBM. Okay, so his investment was in those days $75,000, and they say that this is the most profitable investment made in the history of the economics. Some people say that. Okay, and that's what was happening with the PC side. There were lots of competitors, but IBM was a big player. So everybody kind of got around IBM PC and made compatible computers. In 1960s, okay, many things also were happening outside of the personal computers with the large computers. This guy, he invented the graphical user interface, complete with windows, icons, menus, and mouse. So basically whatever we are using today as the operating system interface, the mouse and the windows and etc., they were all invented during 1960s. Okay. So I mean, as an invention wise, the ideas were there, but they needed very expensive computers that would cost $100,000. But in 1980s and 1990s, people started making personal computers cheaper and more powerful. And then we started running versions of Unix, okay, on Macintosh computers and versions of Unix-like operating systems on Windows computers. Okay, that's what happened with the personal computers. And today we are still continuing on this path. We have the Windows computers. Of course, Windows is not compatible with the MS-DOS computers at all anymore. Okay. And we have the Mac OS. Mac OS is not compatible with the Apple's original operating systems. But they still continue, they keep adding new stuff. Their computers, their operating systems becoming more and more robust, more and more user-friendly, efficient, and open for extension. Okay. Then in 1990s, this mobile computers came up. Nokia kind of started it. Okay. Nokia said that why don't we combine a cell phone with a small computer, personal digital assistant, in 1990s and 9000. Okay. And people liked the idea. In 1997, Ericsson said that, okay, I'm going to call this kind of a computer a smartphone, GS88. Okay. So the smartphone term is invented by Ericsson. And then came the BlackBerry OS, business users, smartphones. Okay. Then Apple's iOS with the iPhone, or the Google's Linux-based Android 2008. Okay, these are the operating systems for the mobile computers, very light computers. For these kind of computers, battery and security management is the key. That's the main motivation. Okay. So, of course, usability is also needed, but security and battery management became the issue. For these kind of computers, interactivity is the issue. I mean, I am not concerned about efficiency with these kind of computers, because as you see, 90% of my CPU, okay, 80% of my CPU is idle. I don't care. I didn't buy this computer to use it very, very efficiently. I didn't pay $2 million to it, right? I don't have to keep it busy, okay? What I'm expecting from this computer is for it to be interactive, okay, user friendly. It should be responsive. When I click some button, it should respond immediately. So interactivity and responsiveness, is the central idea with these PCs, personal computers. So the 5th generation on top of interactive and responsiveness, security and battery management. I don't care about the battery management for a desktop PC, but for a laptop or for a mobile computer, well, they are very, very important. Okay. The nice thing, or maybe I shouldn't say nice. One interesting thing about this history of the operating system study is, okay, when first personal computers started appearing, okay, they had to solve the exact same problems that the initial computers were solving, okay? The initial computers, the operating systems were very, very weak, very, very small, because our computers are not powerful enough to run those operating systems. When they have invented these personal computers, we run into the same problem, okay? Our computers are not powerful enough to run a complicated operating system. So I am using primitive operating systems, okay? When we had first mobile computers, like the cell phones, our cell phone computers were not very powerful, okay? So interactivity suffered, some security issues, and etc. So what I am saying is that when you receive a new generation of computers or operating system, we have to solve the same problem over and over again. Okay, over and over again. I remember writing programs in 1990s for personal computers, and we used to have a crash maybe 2 or 3 times a day, a computer crash, system crash, because we didn't have the protection hardware. Okay, nowadays they are having the same problem for the embedded systems. Embedded systems are very cheap computers, maybe 50-cent CPU, not even $1, 50-cent CPU, 50-cent memory, very cheap computer, but very unpowerful. Okay, so you cannot have protection hardware on it. You cannot have very large, powerful, sophisticated operating system on it. So you are running into the same problem of the 1955's problems of not powerful hardware. So what I mean is that we are going to see the same problems over and over again. And even today, we face the same problems for certain kind of computers that they had in 1950s, 1960s. Okay, so we talked about this. I think that will be the end of discussion about history of the operating systems and computer architecture. At this point, I'd like to show you a video. Where is my video? Yeah, this is, I think I downloaded this from YouTube. This video is made in 1950s. Okay. Can you guys hear the voice?
No, we can't.
No, we can't.
No, you can't. I think I'm going to reshare it with the voice.
Lincoln Laboratory in Lexington, Massachusetts, a major research organization which has played an important role in developing this nation's defense system since World War II. But although Lincoln Laboratory is perhaps best known for its work in radar and advanced warning systems, it is also
Do you guys hear it now?
Yes. Yes, you can.
Yes, sir.
Okay. Yeah, I stopped it. Let me show you this computer. So this is of course, it's a mainframe, it's a large computer. And as you are going to see, it doesn't have any keyboard. They are introducing this idea of sketchpad, which uses a light pen. And that's the initial ideas of communicating with the computer using graphics, not by instructions.
Output equipment here. We have a scope, a knob. These are unusual at the time, and push buttons, toggle switches. We have several other related devices. This made the TX2 a prime candidate for the sketchpad developments back in 1961, and it remained a program in this machine, so it would become a coherent partner in graphics. So
This guy is Sutherland, okay? He is the inventor of the graphical user interfaces in 1960.
the man can communicate with the machine.
Now, how do you actually go about communicating with a computer in a graphical sense?
Well,
He said that communicating with a computer in a graphical sense, that was the very new idea, and it sounded funny in those days.
are using an oscilloscope here, which is much like a TV set, except it's being driven by the computer.
He says it is like the TV set, except it is driven by the computer. So they don't have a term for the terminal. They don't have a term for the screen. It says it's like a TV set, except it is driven by the computer.
In order to get the information into the computer, we have to draw somehow on this display, and we use the light pen. Well, in order to construct a meaningful engineering drawing, we have to have several graphical manipulations.
Does anybody know how light pen works? Light pen. It is connected to the CRT operation. Nobody knows it. Well, I mean, I don't expect that any of you seen light pens before. I did not see one. It's an old technology, but it works much better than what we have today, even with the mouse or the digital pens and etc. Very simple device, but very effective.
Ivan Sutherland's programs can draw straight lines and circles.
Well, that's about what you do in the drafting equipment anyway, isn't it?
That's a very good
Compass,
start.
T square.
In order to do this, we can position this bright spot in the middle of the cross that you notice at a desired location. And we press the button to command the computer to draw a line. It will draw a line from this position where I am now to any subsequent position of my light pen. This is much like a rubber band stuck on two pins. One is nailed on the screen here, and the other is at my light pen. So
These kind of things were revolutionary in those days. I mean, they are like sci-fi movies. Well, I mean, these are like sci-fi movies in 1980s or 1990s, and let alone being them in 1960. 1960 is like a beyond the sci-fi movie.
I can position this anywhere I want. Now, I lost tracking there. I moved the pen too fast, and that told the computer to stop drawing the line. Well, if you notice, that bright dot will jump onto the line as I get close to it.
Well, the dot in the center of the cross, when you get close to the line, jumps over onto it.
Correct.
Why does it do that?
It's much like a gravity field. At the end point, it is even. But it'll allow us to position.
So these are
exactly
the first ideas of the.
I have in mind.
What do you mean?
All right. Here. So I've selected a blank piece of paper, we'll call it. We have several pieces of paper. And I can, let's say I'm beginning to design. I have a very nebulous idea what I want to have in mind. And as I draw my part, let's say on the scope, it reinforces what I have in mind.
So it is kind of describing what computer-aided design software is. So initial versions of the CAD software maybe. And you can have different views of it. Is it going to show it? No, it's not. So maybe you can watch it yourself. Ivan Sutherland, okay, Sketchpad. It is interesting. So the hardware-wise, it was always there if you had the money, but the thing is that to do this kind of stuff at your home computer, it took us some time. And to do these on any of computers, we need the operating system up. That's why operating systems kept changing and changing and changing all the time. And they came to a position that our desktop operating system and our smartphone operating system are very, very different nowadays. They are both complicated, but their problems are so different. As I said before, you don't care much about your desktop operating system's power usage, but it is important for the smartphone or the laptop computer. Okay, you don't run the same operating system in those environments. Okay, good. Any questions so far? Does anybody know who this guy is more? Intel Corporation is more.
Doesn't he have a law?
There is a more law. What is more law?
Is basically every 2 years CPU power is going to double, or number of transistors.
Exactly. So when Moore said this in 1970s, okay, in 1970s he said this, and he's the founder of the Intel Corporation, one of the founders of the Intel Corporation, very smart guy. He saw into the future. He said that, okay, we are going to make microprocessors, CPUs. And I know that the power of the CPU will double every 2 years or 18 months. And they are going to be costing the same $1,000. For $1,000, you can buy 2 times as powerful computer every 2 years. And this trend continued from 1970 to maybe 2010s. Okay. Nowadays it is not going that way because we hit the limit of the useful transistor sizes. We cannot get smaller than certain amount, definitely not below the molecule level, right? So such a smart guy, Moore. I was watching a documentary the other day. When they started producing the Intel CPUs in 1970s, somebody said that, why don't we build computers for the home users using these CPUs? Moore said that, who's going to buy it? And nobody came up with an answer to convince him that a personal computer would be a good thing. So Intel said that we are not going to build a personal computer. We are going to make CPUs, and CPUs will be used by other devices, not by the computers. Okay, so I mean, for us today, you might say that, okay, PCs are the way to go. I mean, it is so logical. You would make lots of money if you built the PC. But even that guy Moore, he could not know that PC would be a good personal computer, would be a good product. People would buy it. In fact, it would be one of the largest industries of the all time, the computer business, etc. He was in the chip business. He was producing the best CPUs of all time, but he didn't believe in the personal computers. So these kind of old documentaries, they will tell you how people thought about the computers and what motivated them to develop whatever we are using today. Okay, sometimes you understand the reasoning why we have 2 or 3 types of personal computers, why we have 3, 4 types of operating systems, and those are mainly historical reasons. Okay, watch those kind of documentaries. They are all available, and usually they talk to the original figures of the the stories like this, like they talk to Bill Gates or Steve Jobs or Engelbart or the Sutherland or the guy who sold this operating system to Bill Gates. IBM went to that guy. Okay, that guy said, "Okay, I am not going to give you my operating system," but Bill Gates did. Okay, this computer. Let me show you this one. Altair 88,000. This computer, let me open the Wikipedia page. Okay. In 1974, it uses the Intel CPU 8080. It's not 8086, but 8080. Okay. This is the first personal computer, actually. It didn't have any operating systems because it is not powerful enough to hold any operating systems. You program this computer through these switches. You turn the switch on and off. Okay. You specify with these switches, you specify the address, and with another set of switches, you specify the data to put in that address, and you put that address in there. Okay. And you program this computer by putting data to the addresses that you specify and tell the CPU run later. Okay, that's how you do this. And in fact, this one was using Intel CPU. Who invented this thing? Okay, he was a doctor, actually, medical doctor. He later became a medical doctor, Ed Roberts, and he did not make any money out of it. He is the inventor of the first PC. Okay, see, he is the father of the personal computer. Okay, so Bill Gates, when he saw this computer, he decided to write the basic interpreter for this computer, and he sold it to this guy, Edward Roberts. Okay, so this interpreter became the first interpreter running on a personal computer. Okay, Bill Gates became a 100 billionaire, right? This guy, no, he did not make much money. In fact, he quit the computer business. As I said before, he became a physician, medical doctor later. Okay, and this is, I guess, yeah, world's first mini computer kit. Well, they don't say microcomputer, it says mini computer. It's a personal computer, okay? And they don't sell it this way. You buy it in pieces and you assemble it yourself, okay? And this is the 1974 Popular Electronics. Later, they added peripherals to it, and this is a typical, okay, setup for this computer. There is a terminal, okay? This one is for printers. You input your data using some tapes or maybe the switches. That was the computer. So read about this and watch the documentary about this one. Later they have added this stuff. See this one? Do you guys find this funny? 1024 word memory board. That means 1 kilobytes of memory for $176. In kit price, if you assemble it, is $200. If you are going to buy 4 kilobytes of memory, it's going to be $300. These were cheap in those days, money. Okay, so if you have a $1,500, you will have a very nice computer. Still no operating system. You cannot run the operating system and the other programs at the same time. Okay, no operating system. Maybe a basic interpreter, but No operating system. Operating system came later when you had enough number of bytes available for you. Okay, so again, read this documentation. Also watch the YouTube documentary movies about this one. It's very interesting. Okay, good. Okay, let me continue with the computer hardware review. This course is about operating system, which is a piece of software. I keep saying this, but operating system needs to know the hardware that is running on. Okay, that's why I need to make a hardware review just to introduce sufficient information to understand what the operating system needs to do. This is a basic, very simplified architecture of a computer system. At the center, we have central processing unit. That central processing unit and memory are connected by a bus, okay? System bus. They communicate over this bus. The width of this bus is dependent on the CPU and the memory capabilities. For the early PCs, it is 8 bits, or it was 16 bits, okay, buses. So you can just read 16 bits from the memory, okay? There are 8-bit processors too, okay? So you address your memory 8-bit by 8-bit, and you can get one 8-bit or 1 byte from the memory at the same time. There is this memory management unit which sits inside the CPU. It is used for virtualizing the memory. So any program running on the CPU would think that they have their own CPU. In fact, they don't. Okay. In fact, they keep sharing this video. CPU communicates with the controller. These are electronic devices through the bus. So CPU communicates with this video controller to show something on this monitor. CPU communicates with the keyboard controller to get some data from the keyboard. Or CPU communicates with the hard disk controller to write data to a hard disk and to read data from the hard disk. Okay, so that's what's happening with the computer system. Everything is connected to this bus, and this bus is controlled by the bus controlling hardware, and CPU operating system has the privilege to control it. Your ordinary programs are not allowed to control these video controller, the keyboard controller, the USB controller. Only the operating system has the privilege to communicate with these controllers. Okay. As an end user program, all I can say is that read some characters from the keyboard. I don't know how it is done. Operating system and the controller does it. Okay, so I'm going to look at this picture one by one. I will start from the CPU, then I will go to memory, then I will talk about a little bit more about these. And I will start with the processor. But it looks like I am out of time. So I'm going to stop at this moment. I will send you some instructions about next week's lecture, how we are going to do it. So watch the Teams page notifications. You are going to see some instructions. Okay, any questions before I end this week's lecture? Any questions?
I have a question.
Sure.
The operating system is designed for hardware specific.
Yes,
I guess.
yeah,
I
yeah.
understand. So I can, for example, run Linux on my computer, which is mainly Windows running without virtual machine. So This is because the two operating system is similar, or I don't know.
Well, I mean, you're okay. The first question is, you have your hardware, okay? This is hardware. On top of the hardware, usually you have hardware abstraction layer. This is how they design the operating system. On top of it, you have the modular operating system or portable operating system. So this modular operating system or the portable operating system would think that the hardware underneath is the same. Doesn't care if the hardware is a Motorola hardware or the Intel hardware or the ARM hardware, okay? So some part of the operating system is portable. I can port it anywhere I like. But this layer has to be specific for that hardware. This is how they design nowadays the operating systems. That's why you see that the same operating system, it can work on ARM processors or it can work on Intel processors. But they made it even more portable by doing this virtualization, virtual machines. Okay. So at the bottom of this picture, there is the hardware and hardware. On top of hardware in your case, let's say you are running Windows operating system. On the Windows operating system, you will have your Teams program, Word program, Excel program, etc. But I can run this hypervisor, okay, to make it look like this guest operating system would think that it is running on a hardware platform like that. So what you're doing is you are running type 2 hypervisor, and the type 2 hypervisor shows itself as a hardware platform. So you are running Linux on top of it. Your guest operating system could have been Macintosh operating system or Mars operating system or some old Windows operating system, doesn't matter, okay? That operating system doesn't know that it is running on some kind of a software, not hardware, okay? This is called virtualization. Nowadays, this is very popular, okay? It's an extension of the operating system idea, right? What does the operating system do? It abstract away the details of the hardware, right? This hypervisor abstract away, okay, the details of how the rings are done. Doesn't matter if it is running those services through the software or hardware, doesn't matter. This guest operating system would think that it is running on real hardware, but it is not actually. Of course, this is software, and this is software. All three has to run, okay, and physically on this hardware, right? That's why it gets more expensive. That's why your virtual boxes is going to run a little bit slow, right? Because it's hypervisor, guest operating system, host operating system, they all at the end has to run on a physical CPU. Okay? Did I answer your question?
Yes, thank you.
Okay, any other question? That was a very good question. There is a chapter in our book. It's called Virtual Machines or Virtualization. If I have time at the end of the semester, I'll talk about it. Otherwise, you would read it yourself. Virtualization, containerization, Dockers, they are very hot topics of nowadays. So you should know about those. Good. Okay, that will be it. I will see you next week.
Thank you. See you next week.
Thank you, sir. Have a nice day. Goodbye.
Bye.
Thank you.
Ah, you are here, right? Bye.